Okay, when you have in the molecular formula, you have a nitrogen. One thing you want to look for is the presence of amines. So let's remember here what is an amine. So here well, that was a nitrogen, NH3, so that is ammonia. So when you have one of the H's here replaced by an R group, you have a primary amine. And if you replace two of the H's in ammonia by an R group, you have a secondary amine. And tertiary amines will have that. So three R groups. What is important is that in the region between, say, 3200, I'm going to center the signal about that. It is about 34. So see, these are the signals for primary amine here and secondary amine here. And so notice that what is the difference? In one case, you have two H's, and you can have one vibrational mode like simultaneously stretching both, or you can have one and not the other staying, and vice versa. So there's two vibrational modes. This is why we in the primary amine have these two signals. So that's very characteristic, and in that region. Also remember that everything hydrogen attached to any other atom will be at least from 2000 and above. And so here is the region for amines. Now, if you have only one H, there is only one stretching mode, that is hydrogen nitrogen. So it's this stretching mode, so coming and going in that direction, but it's on the same region. So secondary amines show there. Now, tertiary amines, no signal in that region because they don't have that H. All right. Now, and this is like summarizing what are the things that you expect to see around 3000. So all of the bonds, again, hydrogen attached to another atom. So in the region 2700 to 4000. But this is typical. So right under 3000, these are the alkanes signals. That's an A, alkane. And that's carbon sp3, hydrogen. That vibration they show in this region. Then right above alkene, and again, you have to see this vibration, you gotta have that hydrogen. Remember that if you have, for example, a tetra substituted alkene, you will not have this signal because you here have a hydrogen R groups in all of them. Same with alkynes. Alkynes will be in about to say 3200 centimeters -1, but this is only for terminal alkynes. If the alkyne is not terminal and you have two R groups, then you lose that signal with the H. Here is what we just analyzed. So two primary amine in this region, you will have two signals. If it is secondary, only one. NOH will be in this region, but shape varies. So hydrogen OH with hydrogen bond, it looks like that. And if there is no hydrogen bonding, so in dilute solution, you may see this. And carboxylic acid is much wider in that region. So in carboxylic acid can cover up all of these, actually, so large. Now, one important thing to determine is the degree of unsaturation. So degree of unsaturation. Also, we call that hydrogen deficiency index. So here you see the normal alkane formula. The general formula is CN H2N plus 2. So double the number of carbon times 2. And so this is pentane. But now if you have pentane, one pentane, now you have 10 hydrogens. So notice this two atoms of hydrogen, or in other words, like a molecule of hydrogen. That is one of these equivalent to one HDI of ones HDI equal 1. So 1 unsaturation. So notice 2 units different. 12 minus 10 is 1 unit, 1 hydrogen molecule. So 1 unsaturation. Here, when you do, say, 12 H's in pentane minus 8, now you have 4 H's difference, which will be 2 molecules of hydrogen. So that is an unsaturation number of 2. Now this is cyclopentane. And if you count now, cyclopentane is C5H10. So the molecular formula of cyclopentane is identical to this. And these are constitutional isomers, but notice having one cycle is equivalent of having one double bond. So unsaturations can be different combinations, triple bond, double bonds, or even cycles. So now, these are the possible combinations. So each of the double bonds here is 1 saturation, so 1 here, and 1 is 2. This is a conjugated diene, and this is actually another diene, but it's cumulated. Cumulated diene. But still you have 1 unsaturation, another. So each double bond counts for 1. Here, each of the pi bonds count for 1. So here you have 1 sigma and 2 pi bonds. So each of the pi bonds is 1 unsaturation. So this is 2 unsaturations, and this is also 2. Difference here is that on the left you have this one is an internal alkyne, and this one right here is a terminal alkyne. This will be different, remember, and this two can be distinguished in IR because this guy here gives a signal about maybe 3200 or so centimeters -1. Now, we just saw before that cyclopentane and pentene has the same number of unsaturation. So you can have one ring counting as 1 unsaturation. So 1 unsaturation can be a double bond or a ring, which is what we did in pentane. So 1, 2, 3, 4, 5. Yeah. So in that case, let's redrawing this. So this is 1 pentane and this is cyclopentane. Both of them share the same molecular formula, so C5H10. And so 1 unsaturation. Now, this is 2 rings, so each of them is 1 unsaturation. So that is 2 unsaturation overall. This combination here is 1 double bond and 1 ring. So it is 2 unsaturation. Here, same. 1 double bond and 1 ring. So 2 unsaturation. Double bond, 1 ring, same in all this case. Okay, now the general formula to calculate the number of unsaturation. Again, you can do degree of unsaturation, the same as hydrogen deficiency index. So 1/2 of the number of carbons times 2 plus 2 plus the number of nitrogen atoms minus the number of hydrogens minus the number of halides. Notice that oxygen is not in that formula. It does not affect that. Okay, so we need to remember this formula because it will give us an idea of what we have in the molecule. Now let's apply to what we did to this problem right here. So here we have a molecular formula C5H10O. So let's calculate the HDI. HDI, hydrogen deficiency index, is 1/2. Now the number of carbons is 5. So 2 times that is 10, and then plus 2 minus the number of H's, which is 10. I don't have halides, oxygen doesn't count, so this is 0, and now 2/2, that's 1 unsaturation. Now, analyzing the molecules here, this molecule A has 1 unsaturation because it has a double bond. Molecule B has 1 unsaturation because it has a ring. Molecule C has 1 unsaturation, a double bond. D has 0 unsaturation, so I can cross that because it's got to match this formula. Also, you can count the number of carbons, hydrogen, and you will see that it doesn't match. So molecule D, I'm going to cross. Now, molecule E has 1 ring, so that's 1 unsaturation. So I have now 4 molecules. Now, expecting the spectrum, I'm going to draw that line. Well, it wasn't straight, but right here in this region is like alkane type, so carbon is sp3, hydrogen is attached to carbon is sp3. But this band here is an OH. So that in here is an OH that with hydrogen bonding, and likely this is also OH. And remember, of course, we have oxygen in the molecule. We cannot suggest an OH if we didn't have one. So this is say free, so no hydrogen bonding. In a more diluted solution, you will see that. And this is brother, so is that. So now my molecule needs to have 1 saturation and 1 alcohol. So A is not an alcohol, I'm crossing that. B is an ether, so I'm cross that. C is an aldehyde, so it's not, so my final answer is E, which is 1 saturation, the ring, and the alcohol. So one more problem in the same direction. So here you have the molecular formula C6H12 in O. So HDI is going to be my degree of unsaturation, 1/2. And so 2 times the number of carbons, so that's 12 plus 2 minus the number of hydrogen, so that's 12. Oxygen doesn't count, so I'm going to cancel those. So again, that's 1 unsaturation. Analyzing the molecules, here the first one has 1 ring, so 1 unsaturation. B has 0 unsaturation, so I'm going to cross that. Here I have in the molecule C, I have 2 oxygen atoms, so that doesn't match my molecular formula. So I cross that one. Now, next one, here you have 1 unsaturation, that's good. So that could be. That's 1 possible and only 1 oxygen. Here, molecule E has 1 unsaturation because we have a ring. And so it's also possible. Now, looking at the spectrum, molecule D is a carbonyl compound, so it's a ketone, and this is an alcohol. And we see that we don't have any of the alcohol bonds, so the alcohol would be here and it's not. So I'm crossing that. Let's check if we have the carbonyl band, and we do. About here, this is the peak, this is due to the stretch of that bond. So now we have, notice how we ruled out some of the molecules. First step then, do the HDI and then see what matches the molecules that you've been proposed. Also need to match the molecular formula. Notice that molecule C had, had actually 2 unsaturation, 1 of the double bond and 1 of the ring. So it didn't match that and didn't match the number of oxygen. So we crossed that. So, and the only 2 options of 1 unsaturations were D and E, but E is an alcohol and we don't have this in this spectrum. Instead, we have a carbonyl band, so it is molecule D.